Howdy y'all, welcome to the Science of Sound. So, before we get into the science of sound, we should talk about what a wave is. So, to start off, a wave is traveling, vibrating disturbance by which energy, not mass, is transmitted without matter. Now, there are also different kinds of waves. To start off, we have the transverse wave. This is a motional wave that moves differently from medium waves. This includes ripples that you see on the water and traditional radio waves. Next, we have the longitudinal wave. This is a motional wave that moves in same direction as medium waves. This refers to sound waves, which we'll get into, and seismic P waves. Okay, so now we talk about sound waves. And sound waves are a disturbance caused by the movement of energy through air and water away from a sound. The definition we used in class was that vocal cords moving air molecules back and forth. So this is like when somebody's singing, as seen here. Could you demonstrate that, please? So real quick, let's go over some properties of waves. So first we start with wavelength. This is the distance between identical points on a wave. This can be measured in nanometers, centimeters, and meters. And then we've got amplitude, which is the vertical distance from the midline of the wave up onto the peak of the wave. And then velocity, as you may be familiar with, is the speed and distance that a wave can travel through space. Now we're going to get into the science of sound, and the best way to demonstrate that is with instruments. So as we talked before, wavelength is the distance between 2 points on a wave, and that distance kind of plays into frequencies and how certain pitches sound, because if you have a longer wavelength, then you're going to have a lower frequency, which is going to result in a lower pitch. So if I were to play C, or B, those are low pitches on the saxophone. So therefore, they're going to have a low frequency and a very long wavelength. Now, if we were to go to the opposite side, a shorter wavelength would have a higher frequency, which would result in a higher pitch. So if I were to play this, D, E, and F sharp all were very high. So these high pitches will end up having very high frequencies at very shorter wavelengths than our lower pitches. And this plays into how instruments are made, because high frequency, higher pitches would be more common on a shorter instrument, like as we talked in class, piccolos and tubas, and then as we lengthen the instrument, it will produce a lower frequency sound at a lower pitch, just like I demonstrated on the alto. And it also varies with different sizes of instruments. So the alto here in my left hand will have higher pitches and higher frequencies than the tenor sax will in my right hand, which would produce a lower sound at longer wavelengths than the alto would. Same would go for bari. Bari would be even lower frequency than the tenor, and the soprano would have an even higher frequency than the alto. So as we just discussed before, vertical distance from the midline to the peak of the wave is known as our amplitude. And volume is very dependent on the amplitude. So if you're going to have a louder sound, you're going to have a higher amplitude on your wave. And if you were to reverse that, a softer sound would result in a lower amplitude on your wave. So we just covered how the science of sound is meticulous in the creation of instruments. It is also helpful when in the creation of music halls, such as our very own Beston Hall at Nazareth College. However, what happens when you have the dead space and other spaces where it's really louder, when you're listening to a symphony or a jazz band in the concert hall? Well, to explain this, we're going to talk about interference. So, interference is what is happening when waves from two different sources come together at the same point. There are two types of interference, constructive and destructive interference. Constructive interference is when wave amplitudes add together. This is where you have your louder sections in the concert hall. And destructive interference is when the wave amplitudes cancel each other out. So this is where you would get your areas within the auditorium or music hall where you would have some dead space, much like these videos here. So that last video was pretty annoying, right? Well, that video had everything to do with the Doppler effect. Now, the Doppler effect is the way a frequency of a wave changes if there is relative motion between the wave source and the observer of the source. This kind of concept has many uses in daily life. It is used in police radar, catching speeders, bats through their echolocation to find each other, and meteorologists as they predict the weather. And in the Doppler effect, the speed of the source is always the same. It's only the frequency length that changes. So, with that said, if we go back to the video, we have the person here. This would be considered our observer when we talk about the Doppler effect. The car here is the wave source which the sound waves are coming from. So, as the car is farther away from the person, then this results in a low frequency, longer wavelength of sound. But as the car gradually gets closer to the person, then the wavelength, the frequency of the wavelength will increase and the wavelength will get much shorter, resulting in the higher pitch. Then as the car continues on down the road past the observer, the frequency becomes lower and the wavelength once again becomes longer as the pitch will gradually get lower until it is out of the observer's field. Well, that's the end of this video. Have a good day, y'all.